Hi everyone, I'm going to share our paper to you. It is gradient-based parameter selection for efficient fine-tuning. First of all, let's say what is parameter efficient fine-tuning. Given the increasing size of pre-trained model, fine-tuning all the parameters in the model is memory intensive and data inefficient when fine-tuning multiple downstream tasks. So the PEFT method aims to fine-tune a minimal number of parameters to fit downstream tasks, while keeps most of parameters frozen. There are some typical methods, for example, adapter, LoRa, VPT, wheel pump tuning. However, this kind of method have some limitation. First, they introducing the additional learnable parameter into the backbone that leads to disrupting the original architecture and increasing computational costs during the training or inference stage. The last limitation is this kind of method lack of generalizability across various model architecture. For example, for the wheel pump tuning, they introduce the learnable vector into the input space of transformer, which is perfect in the transformer, but it's hard to be applied to CNN because it's hard to introduce the learnable vector into the input space of CNN. In order to address the above limitation, we propose a novel method. This is overview of our method. So first we select parameter from the original model, and then we just fine-tune this selected parameter and keep remaining parameters fixed. Doing this, our method can be model agnostic, and we didn't introduce any parameter during the both training stage and inference stage. And our method is task adaptive because we select different parameter for different tasks. Next, let's say how we select parameters. We consider two aspects. The first one is the importance of the downstream tasks. We identify the gradient value as the importance matrix because parameter with largest gradient value indicates the fast change in loss function along the gradient direction. And the second one is we think every neuron in a network should be involved because it can potentially adjust all the neuron states to better fit a task during the fine-tuning stage. So we combining these two aspects for fine-tuning. Specifically for certain tasks, we first calculate the gradient for all model parameters. Then, for each neuron in the network, we select top K connection with the highest gradient value among all the input connections to that neuron. For example, the figure A is a case that we select top 1 input connection per neuron, and figure B is a top 2 case. And let's say our method again. So first we have a pre-trained model, and then we calculate the gradient for one task. And then based on this kind of gradient, we select the parameter per neuron. And then we can get a binary mask in here, which indicate which parameter is selected, which parameter isn't. And during the fine-tuning, we can use this parameter to we can use this mask to set the gradient of unimportant parameter to 0. And let's say how our method works. This is image classification benchmark FGVC. As we can see, our method achieved best result over all 5 tasks. And this is another image classification benchmark VTAB. It contains 19 tasks. For most of tasks, our method achieved the best, and our method achieved 1% improvement on average accuracy compared with the SOTA. And we also conduct experiment on semantic segmentation. As we can see in here, our method can handle some difficult case, like in here. Our GPS is most close to the ground truth. And we also evaluate different architecture, including VIT. It is a transformer-based architecture, and swing transformer. It's another version of transformer. And we also test the CNN-based model. And for these 3 architecture, our method achieved the best accuracy on average. Thank you for your attention.